Okay, this is our last topic of the year, and we're kind of doing something we did last week, which was the slope fields. We're going to do something a little bit different today with the slope fields. We're going to try to match the given slope field. So you can see we have a slope field over here, and we're going to try to match it with one of these choices down here. They give us 10 choices, and we got to figure out which one is the correct one. Now, the correct answer is actually not listed below. This is the correct answer for this slope field. But this is the kind of question you would get. They would give you a bunch of choices, and you have to choose the right one. So we're going to take a look at this slope field, and we're going to start crossing off some of these choices here. And I'm going to explain why we're going to start crossing some of these choices off. So it looks like there's a ton of answers. There's 10 answers down here, but we're going to be able to cross off a lot of them all at once. So let me explain what I'm talking about here. The first reason that we can start canceling a bunch of choices is if it depends only on x. This one says that our derivative, which is our slope, is equal to x minus 3. So you'll notice it only depends on x. So when something only depends on x, the slopes will be the same for any given x value. So for example, when x is 1, you're going to get a slope of -2, but it doesn't matter what the y value is. Every single y value is giving you the same exact slope for that given x. Let's look at another one. When x is 4, this is another example. Every single one of these slopes, doesn't matter what the y value is, if the x is 4, you're getting a slope of 1. So we say that this depends only on x because your slope is equal to a function of x. And when that happens, you're going to see the same exact slope going up and down. It doesn't matter what the x value is. If you go up and down, you should see the exact same slope for that given x value. Now, if you look at the choices below, anything with a y can basically be crossed off. We can cross off anything with a y because this slope only depends on x. So we're canceling anything with a y. And so we've crossed off half of our choices. Okay, the next thing I'd like to look at is when you have a 0 or undefined slope. So you can see we have a 0 slope when x is equal to 3. So we can start plugging into these and seeing if we get a slope of 0. And when I plug in a 3 right here, I do not get 0. So I can cross this one off. When I plug a 3 into here, I get 1/3. That's not going to work. Plug a 3 here, you get 9, so that's no good. If you plug in a 3 here, you just get 3. So you can see I'm crossing all of these things out. Cosine of 3, we're assuming it's 3 radians. That's not going to give us a 0. So, I mean, here's the real answer for this particular question. When I plug in a 3 for the x, I get 3 minus 3, which is 0. And so that's how I'm getting the slope of 0 here. When I plug in a number that's bigger than 3, I get a positive. So you see all the slopes over here are positive. And when I plug in a number that's less than 3, I get negative. And that's why when x is less than 3, all these slopes are negative. So that's one thing we could look at when we're trying to figure out which one of these choices below matches with this given slope field. Again, for these first couple examples, the answer for the given slope field is not going to be one of these choices. So I'm just telling you this is the answer for this particular slope field. Now let's look at a different example. What if you had dy dx is equal to a function of y, so it only depends on y? When your slope only depends on y, you would get the same exact slope going left to right. So it only depends on that y value. It doesn't matter what the x is. So this x value and this x value and this x value, they all have the exact same slope as long as their y value is the same. So it only depends on the y. So when you see a slope that's equal to a function of y, you should expect to see the slopes have the exact same slope going left to right. So if I was going to start crossing things off at the bottom, if I just saw this picture here, I would say, hey, each y value has the exact same slope going all the way from the left side all the way to the right side. So this slope field only depends on y. So anything with an x can be crossed off. All right, I'm only left with one possibility. And I can check what happens when y equals -1. I'm expecting a slope of 0. Does that happen? Well, for this one, when y is 0, I get a slope of 0. Not when y is -1. So I would cross this one off as well. Again, we already knew that the answer was not one of those 10 choices. The answer is sitting right here. But this could be one of those choices. And so how would we know that this slope field goes with this slope right here, this differential equation? Well, one of the things I would do is I would first notice that every slope is the same going from left to right. So all of these slopes are the same, all of these slopes are the same, all of these slopes are the same. So it only depends on y. So I would look for a differential equation that was just a function of y. Then I would look to see where I knew the slope was 0. That would be at this spot here when y is -1. So I would plug in y equals -1 and see if any of them gave me a 0. On this one, if I plug in a y equals -1, I do get 0. So that would be a good choice. You could check a couple other spots. When y is 2, do you get positive? Yes. If I plug in a 2, I get a slope of 3. And if I plug in a -2, do I get a negative slope? Yes. When you plug in a -2, you get -2 plus 1, which is -1. So everything looks correct. All right, now we're going to do some real examples, and our choices will be somewhere in these boxes here. So let's do an actual example. So now the slope really is one of these choices in here, and we have to figure out which one. What I want you to notice is that we do not have a function of just x or just y. So if you see anything with only an x or only a y, you can cross it off. So I'm going to cross off anything with just an x or just a y. That leaves me with 4 choices. The next thing I can do is I can look to see where is my slope 0 and where is my slope undefined. I'm getting an undefined slope on the x-axis, and that's when y is 0. I'm getting a slope of 0 on the y-axis, and that's when x is 0. So I need to have x over y so that it's undefined when y is 0, and it's 0 when x is 0. So I need an x over y. So I'm not sure if it's positive x over y or if it's negative x over y, but I know I want x over y. So I'm going to cross off C, I'm going to cross off D. So it's got to be one of these. It's either x over y or negative x over y. How do I decide which one? So now I'm going to look at the top up here. You just want to see where is the slope positive and where is the slope negative. And I usually try to go with quadrant 1. You'll notice every slope in quadrant 1 is positive. So if I plug in the 0.11, just as an example, I should expect to get a positive slope. So the 0.11 is approximately here. If I plug a 1 into this, I get -1. That's not what I want. So I'm going to cross off B. If I plug a 1 into this, I do get a positive. So that's the one I'm looking for. So I'm looking for A. So our final answer is A, which is going to be dy dx is equal to x over y. All right, let's go ahead and look at another example. This is a similar example. Again, I want you to notice that the slope is undefined on the x-axis. So that means when y is 0, our slope is undefined. And our slope is 0 on the y-axis. That's when x is 0. So we need to have an x over a y. And then look in quadrant 1. Every slope is negative in quadrant 1. So which one of these would I have every slope be negative in quadrant 1? So again, I usually try to plug in the 0.11. If I plug in 1, this one would give me positive, and this one would give me negative. And I want negative, so I want B. So B is going to be the final answer for this one. So for the last 2 examples, we took a look at where is the slope positive or negative. And we also looked to see where the slope was either 0 or undefined. And that helped us decide the correct choice. So they're giving us the slope field, and we have to match the correct differential equation. So we need to eliminate a bunch of them, or we just need to figure out based on where the slope is 0 and undefined, if the x is on top or the y is on the bottom or that kind of stuff. All right, let's go ahead and look at our next example. All right, now there's going to be another way that you could possibly figure out one of these choices down here below. And that is by actually just drawing the function right on the slope field. So for example, try to draw some kind of recognizable function on the actual slope field itself. What does this function look like? The function that I just drew, you can see it kind of goes through pi right here, goes through 0, and obviously it would continue on in each direction. something like this. You just follow the slope field the best you can. I think many people recognize this as just sine of x. So the function that you actually draw on the slope field would be the original function. And if I do the derivative, that would be the differential equation that I'm actually looking for. So in this case, we would say h would be the correct answer. All right, let's check. Let's click on the answer. Yes. And I want you to notice that there is a plus c here because we could draw that same sine function a little bit higher, or we could draw it a little bit lower. And of course, it would continue on in each direction. You want to just do your best to follow the slope field. So in this example, we were able to draw the sine function right on the slope field. So that would be the original function. And then when we do the derivative, we would get cosine. But the derivative is the differential equation that we're looking for. It says dy dx is equal to cosine of x. Let's look at another one of these. Here's another example. See if you can figure out what this function is that I'm about to draw. I'm going to go through one right here. I'm going to follow the slope field the best I can. Of course, I'm just doing this freehand, so I'm not doing a very good job, but something like this. What does that look like? That's y equals e to the x. And I could do like a -2 if I want. -2 would go through right here, but it would basically be the exact same thing, but just down 2. So that would be the original function. And if I did the derivative, I would just get e to the x. So let's click on the answer, see what we get. All right, there we go. I think we got it right. The original function is e to the x plus a constant. And after you do the derivative, you just get e to the x. So we would choose letter E. So what I'm saying is if you draw the original function right on the slope field, and if you could figure out what that function is, you can do the derivative, and that's the differential equation that you're looking for. So in this example, we were looking for dy dx is equal to e to the x. All right, let's look at one more example of these. All right, I think I know one that I could draw right here. I'm going to plot a few points here. It's going to be something like this, something like this. What does this function look like? So that looks kind of like an x to the third function, say cubic function. Now it could be 1/3 x to the third, and if I did the derivative, I would just get x squared, and that's if there was a 1/3, and there's no way for us to know if there's a 1/3 just by looking at the slope field. But if there was a 1/3 in front, then my derivative would just be x squared. So let's click on the answer key. For sure, it looks like some kind of cubic function. And if we did the derivative, we'd get some kind of x squared function. So if it was actually just x to the third, then the derivative would be 3x squared. But the idea is that it's an x squared function. We're looking for the derivative to equal something with an x squared, and I would go with letter G for this one. Again, the function that you draw is the original function. We'll call it y. And then you got to do the derivative in order to get the differential equation. The derivative gave us some kind of x squared, so I'm choosing the one that has an x squared in it, choosing letter G. So that's another way that you possibly could figure out which differential equation goes with the given slope field. So it's just another way that you could think about it and figure it out. All right, let's go ahead and look at our last topic. We'll go to the next page. Okay, for our very last topic, we're going to go ahead and draw particular solutions. They're going to give us a point, so our particular solution must go through that point. And we have to draw a continuous differentiable function on a single open interval that contains that point. So those are the 5 things we're looking for when we draw our particular solution. So they're going to give us a slope field. Let's have a look. Here's our first example. They give you this slope field and they say it has to go through this point, 3, -2. So we're going to draw a particular solution that goes through that point. And so basically all you want to do is just follow these slope fields the best that you can. Whenever you touch a slope field, just stay on that same path. Don't turn at all when you touch a slope field. And it doesn't have to be perfect, so you just do the best that you can. This one looks like it's going to be some kind of x squared function. Of course, I'm drawing this freehand, so it's not very good, but you just follow it the best that you can. Something like this. Let's see if we can find a more difficult example. There we go. We have to go through the point 3, -2, which is right over here. You got to be really careful. Again, all we're doing is just kind of following these slope lines the best that we can. It's going to be something like this. Doesn't have to be perfect, but if you touch a slope line, and just stay on that slope line. You don't want to cross through at a weird angle. Now I want you to see that there is a slope of 0 right here when y equals -1. And so what happens is it's kind of like an asymptote. So we're going to get closer and closer and closer to that line, but we're never actually going to touch it. So this is going to be kind of hard to draw. You just do the best that you can. It's going to be something like this. There we go. I'm just making it a little bit thicker, a little bit easier to see. Now I want you to notice that this is a continuous differentiable function. It is drawn on a single open interval, and it does contain the point that they gave us. All right, so this is another kind of easy one. Let's look at another example. All right, this is x over y, which is going to be a hyperbola. If we draw the entire thing, which we're not supposed to, it will look something like this. I have the right side, I have the left side, and that would be the entire hyperbola. But remember, it has to be on a single open interval that contains that point. So the point's over here, so we're going to choose the right side. We're going to get rid of the left side. There we go. It also has to be a function. So you can see this does not pass the vertical line test. And again, since my point is at the bottom, I'm going to get rid of the top part of it. Now it does have to be differentiable, and it also has to be on an open interval. And that's the reason why I'm going to leave an open circle right here where there's vertical tangent line. Now sometimes the AP test will not have these vertical tangent lines drawn. So you may have to look at the actual differential equation itself to see that when y is 0, your slope is undefined. Notice I'm putting an arrow on the end over here, which says that the function continues forever in that direction. Notice it does go through my point, and anytime you hit an undefined slope or a vertical tangent line, you need to stop and just put an open circle there. So we should have an open circle here. Let's go look at another one. I think most people can recognize this as a circle. If I drew the entire circle, it might look something like this. Of course, this is not a function, right? It doesn't pass the vertical line test. Crosses more than once, so that's not a function. So I need a function. I'm going to erase the top half of the circle. And of course, I'm going to need open circles right here and an open circle right there. Again, you always want to ask yourself, is this a continuous differentiable function? And I would say yes. Is it drawn on a single open interval? And does it go through the point they gave you? The answer is yes. So this would be a good answer. Here's another one. Again, all you want to do is start at your point and just follow the slope lines the best that you can. It's not going to be perfect. Don't worry about that. Just draw it the best that you can, and also in both directions. It's going to be something like this. It's going to be something like this. I'm just going to put arrows on the end, which means that it doesn't stop. It continues on in each direction. Again, this is a particular solution that goes through this point. You'll notice that it is a continuous differentiable function. It is drawn on a single open interval. All right, let's go look at another example. Again, you don't have to know what the function is in order to draw it. You just follow these slope lines the best that you can. So it's going to be something like this. It doesn't have to be perfect. Just look at all these slope lines and just follow them the best that you can. Again, this is a continuous differentiable function. It's drawn on a single open interval, and it does contain the point -3, -2. Let's go look at another example. I'm just going to draw this and follow those lines the best I possibly can. It's not going to be perfect. Don't worry about it. It's going to be something like this. Again, this is a continuous differentiable function. It's drawn on a single open interval, and it does contain the point 1, -2. Let's go to the next one. All right, this is our last example, and it's just kind of a puzzle example, and we're trying to say what functions would satisfy this differential equation. And this differential equation basically says that y prime is equal to y. So what function, when you do the derivative, do you get the same thing back? So how many functions can you think of that when you do the derivative, you just get the same thing back? Well, one of them is e to the x. E to the x looks something like this. Another one is negative e to the x. Negative e to the x looks something like this. And there's one more I can think of, and that would be y equals 0. Y equals 0 is just the x-axis. When you do the derivative of 0, you get 0 back. There are also a lot of variations, like if you had y equals e to the x minus 1. And if you did the derivative, you would get e to the x minus 1 again. So that would be shifting it right 1. That would look like this. It would go through the point 1, 1. So that's why you see all these other slope lines in here. Same thing for the bottom. That's why you see all these extra slope lines. It's because you could shift these left or right, and those functions would also work. All right, that's it for today.